Okay, there is one special case when comparing means. Where you don't do business as usual. And this is when we have paired data. Okay, so somehow in the design of your experiment, you either have like kind of matched pair design, or twins, or same subject with treatment and without treatment. Okay, so these are like the types of situations that can cause that to happen. Okay, so what we do here is you're going to end up with two sets of data that have the exact same data points, same number of data points, right? And what we're going to do, so we'll call, I don't know, the first set of data, let's call it L1, right? And the second set of data will be L2. Okay, and normally what we would do is we'd say, okay, these are like two populations, and do a do a sample of this one, do a sample of that one, and then do a two sample interval or a two sample t-test and draw inferences. But because we're paired or twinned or same subject, things like this, there's a reason to believe that these things are correlated. You've got all these data points, right? So you have like x11, x12, x13, x1n, x21, x22, x23, down to x2n. And what we're going to do is we're going to create a pool called diff, D-I-F-F. And this is literally going to be the value x11 minus x21. Each of the paired values, x12 minus x22, x13 minus x23, and x1n minus x2n. And this is going to give me a single reality, right? So what I'm envisioning this as is that this is the population, right? That we're sampling from. So this is the population of one half of the twins, and this is the population of the other half of the twins, and this is the difference of the values between like selected twins within that population. Okay. So how do we handle this? Well, what we do is this now reduces to a single population called diff. Okay? So what we're going to want is we're going to want to know, make inferences about mu of the difference and the standard deviation of the difference. Okay? But the nice thing about this is that we already know how to do all of this, right? How to take a confidence interval and things like this. So in most cases, what we care about is when mu of the difference is 0, right? Because that means that these populations don't have anything different about them, right? Which means like if you have like the with treatment and without treatment, then the treatment's not doing anything if the mean difference is 0, right? So let's dig a little bit further here. All right, so we have this new population called diff, right? And it has a mean, and it has a standard deviation, right? So if I sample the differences, right? So, and I can find, x bar of the differences, right? I can find a standard deviation of the differences, right? And then I would have the size of the sample of the differences that I am taking, right? This should be, so the x bars should ideally are going to be a t distribution, right? That are going to be centered on the mean of the population of differences, right? So the x bar diffs are going to be centered at the mean, with the t distribution is now going to put me a standard deviation of the diffs over n diffs, standard errors, right, is going to be my thing here. So I'm going to get a nice bell-shaped, but I have to meet the three conditions, right? One, n diff has to be less than 0.10 big N diff, right? Two, the sampling has to be random. I probably put these in a different order in the notes. And three, you either have to be large sample, right, and greater than or equal to 30, or normal diff. So the population of the diffs has to be normal. Okay, you have to have some sort of evidence to support that. Okay, so that being said, like, the confidence interval then is just x bar diff plus or minus some t star value based on my c percentage, right, times my standard error, which is, this should be a square root, there we go, should be s diff over square root of n diff. Like, this should not feel all that different, right? Or if I'm doing a, what do you call it, a significance test, right, I should be, well, the x bar diff, and we're going to test against 0 over the number of standard errors, so that'll be s diff over square root of n diff. And again, we failed to reject the null if, like, the probability of getting a t value like this or less or more extreme is less than my alpha, which we tend to like make something like 5%. Okay, so let's look at some actual sample data here. So let me pull up an example. Okay, so this is some data, and I think what we have here is we've got 11 people who all have are like regular coffee drinkers, and we're going to determine whether or not they're like addicted to caffeine, right? So we're going to randomize an experiment here, and some of them we're going to give caffeine pills to, and some of them we're going to give placebo to. And what we're going to do is, like, some of them we're going to give the caffeine to first and the placebo to first, and then randomly we're going to pick people who are going to be the other way around, right? So this is like kind of a random paired design. So we have 11 subjects, and then we're going to like measure their depression level. So when we give them the caffeine pill, is it lower than when we give them the placebo, right? And same subject, different treatments leads me to a paired design. Okay, so what I need to do is I need to load this all into my calculator. So I'm going to use a little bit of video magic here and actually just do that behind the scenes. All right, so I put the caffeine results there in L1. I put the placebo results hanging out there in L2. Now I need to create the diff the diff sample X. So I need the diffs, right? So what I'm going to do here is I'm going to go back to my main screen, and I'm going to say take L1, subtract L2, and store that in L3. So I've taken the difference of each item in L1 and each item in L2 that are pairs, subtract them, and now I make an L3, which is now going to be my diffs, right? So if I go to stat, edit, those values are now hanging out there in L3. All right, so just by looking at the data without drawing too many inferences, it looks like people who have the caffeine pill have like significantly lower depression rates here, except for one weirdo at the bottom who seems to like be more depressed on caffeine. All right, so whatever, we're gonna deal with that. So like the question is, it's like, do we have enough evidence to say that the caffeine pill is actually, treating or causing the depression to decrease in these people who are probably addicted to coffee? All right, so one way to handle this is to see, like, is zero on the interval, right? So rather than dealing with L1 and L2 separately, I can leverage the fact that I have paired data and just run a one sample T interval on L3. So let me go ahead and do that. I'm going to stat tests, and I'm going to go one sample T interval. Oh, that's two sample T interval. Just a T interval. That's what I want. A T interval. And I'm going to do this with data, which are now housed in L3, my diff thing. Let's do it with a 95% confidence interval. Cool. All right. And there's my result. The diff has to be somewhere between negative 12 and negative 2.7, right? So nowhere in that is zero. So at the end of the day, I believe that the caffeine pill is actually doing something to the level of, what do you call it? The level of, the level of depression that these people are experiencing, right? So I have evidence to support the null, fail to reject the null, whatever we want to call it there. And we'll go there. So this is like the mean diff. This is the standard deviation diff. There were 11. All right, so like how would a hypothesis test go here, right? So let's create a couple of hypotheses. Let's say we want to know if the caffeine's actually having an effect. So my H null is going to be that the mean diff is equal to 0. My H null, my HA is going to be that the mean diff. And for the sake of this argument, let's make it less than 0, because that's what looks like is going on here. And we'll do a significance level of alpha at 0.05. Seems like a pretty good one to work with. So we need to create a p-value here, right? So I bring up the calculator and I go stat test. I'm going to do a t-test. I'm going to do it from the data. My mu is 0, because that's what I want. No difference, 0. L3, I can do a less than, right? And I can calculate. And there we go. We got this t-value of like negative 3.53, which is like way far to the left, right? My p-value here is 0.0027, right? So my p-value is 0.0027. So the p-value is really small in comparison to the alpha. So we're going to reject the null, right? We're going to reject the null right there. I hope earlier I said that we should reject the null as H null. If I did not, whoops, I'm sorry. But let me clean that up now. Like, if the H null is assumed to be 0, then we should be rejecting it here. Yeah. Alright, so we're going to reject an H null. Our claim that these guys are actually, caffeinated is problematic, or is the reality, right? That there's like something, that the caffeine pill is doing something here, right? That it's not 0, it's definitely less than 0 is the mean difference. So there you go. Like, if you think about this, this is actually a little bit simpler than the two sample t-test, but you can only use this in a special case when the data is paired, right? So either both data points are coming from the same subject somehow, or you have a matched pair design, or you have twinning, which is, at this point, you can see you get a little bit more control over things. All right, so there you go.